We're going to be discussing the bonding notes posted on your Google Classroom. And that starts off with just discussing what bonding is. So bonding is when two nuclei are attracted to one another via their electrons, and they form a new compound together. Generally, this occurs, nature actually favors bonding because when an atom is separate from one another, it's a single atom. So let's say we have a hydrogen here and a hydrogen here. These atoms have a high potential energy. So it's similar to having, let's say, a ball sitting on the top of a hill. And because this ball is sitting on the top of the hill, it has a huge amount of potential energy. At some point, when this ball is pushed, so this is a high PE, high potential energy. When this ball is pushed, it will roll down this hill and settle down here at the bottom, resulting in a lower potential energy. It is the same thing that occurs when two atoms make a bond with one another. So when they come together, they are going to bond with one another, and that's going to cause a release of energy. And when they do this, that is why they will more likely be bonded than to be separate, because nature favors the lower energy. Most of the time, when an atom will bond without any energy added, this is oftentimes called a spontaneous reaction. And a spontaneous reaction is going to occur because it is going to release energy. And just like in physics or anything, when something is going to lower its energy as it occurs, that's what's going to take place more often in nature than not. So what actually determines how atoms bond is electronegativity. So electronegativity is how attractive electrons are. An atom is two electrons. So the attractiveness of an atom to electrons. So if we look at the chart, the electronegativity chart, which actually looks like this, you will see that fluorine is, as we might say, the hottest element around. It has an electronegativity of 4. That means that electrons always want to go to fluorine. So fluorine is going to be the top dog of electronegativity. So when we look at the spectrum of electronegativity, and we're going to abbreviate this EN, mainly because it's a long word and you don't want to write that. When we look at that spectrum of electronegativity, you're going to see that we have fluorine on the very high electronegativity, and on the low electronegativity we have francium, and it just increases from there. So this is the low electronegativity. Now, you'll also notice that in general, metals have a lower electronegativity and non-metals have a higher electronegativity. And this is just a periodic trend that you will see take place in this chart. Oxygen is going to be number 2 right behind fluorine, and then we've got nitrogen and chlorine and sulfur and carbon and so on and so forth. Over here, if you see francium and cesium, rubidium, potassium, sodium, all of these are very low as well. Hydrogen, don't forget, is a nonmetal, but it is over here, and it's got a 2.1, which is a much higher compared to all of the other elements over on this side. So if you look at your electronegativity, and you look at atoms that are going to create bonds, we are going to create a bond, and what's going to happen is one atom is going to work with another atom to complete their outer shell. So we have discussed the valence electrons before, and we do have a word for this. This is actually called the octet rule. Octet rule. And this is the elements desire / ability to complete its outer shell to be like a noble gas. So this is your octet rule. So let's say that we are now looking at two elements, then we want to see what type of bond that they are going to create. So we're going to go in there and throw in fluorine, and we're going to also discuss hydrogen. So we would go over here to our chart, and we would look at what our two electronegativities would be, and we would find that fluorine is a 4 and hydrogen is a 2.1. We could also talk here about a couple other elements, and let's talk about sodium and oxygen, and how about calcium and sulfur. And one more, which would be carbon and hydrogen. Okay, so given that we just picked those, we need to find our electronegativities. So this is 0.9. Oxygen is 3.5. Calcium is 1.3. Sulfur is going to be 2.5, and hydrogen is going to be 2.1, and carbon is going to be 2.5. So now we have our electronegativities, and what we're going to do to determine what type of bond we're going to create with these elements is we need to find the difference between the electronegativities. So in this case, we're just going to subtract the highest from the lowest. So to find the difference, you subtract that. So this is going to be 4 minus 2.1. This is going to be 3.5 minus 0.9. This is going to be 2.5 minus 1.3. And this is going to be 2.5 minus 2.1. And doing that math, we're here going to have 1.9. Here we're going to have 0.4. Here we're going to have 2.6, and here we're going to have 1.2. If we go ahead and look at the notes that you were given, you will see right here, if we zoom in right here, that based on this, 0 to 0.3 are nonpolar covalent. 0.31 to 1.7 are polar covalent, and 1.8 to 3.3 are ionic. And so in this case, one more time, I'm going to just show that while I determine these. Hydrogen and fluorine was a 1.9, so that's going to give us an ionic. Sodium and oxygen was a 2.6, so that's also going to be ionic. Calcium and sulfur was a 1.2, so that's going to be a more covalent, very close to ionic. And hydrogen and carbon are going to be a covalent. So given that, we could now figure out. And so the difference is that ionic bonds are going to have a very particular characteristics to them. They're generally going to be solid at room temperature. They're generally going to have a very crystalline structure. They're going to have a high melting point, so on and so forth, versus covalent bonds, on the other hand, are also going to have a particular characteristics. And that on the chart, if you notice, is at 5% covalent or 5% ionic or 50% ionic, that's what it's going to be discussing. Please remember that there are always exceptions to the rules that we are discussing. We're just more talking in general, such as hydrogen and fluorine, when they do come together, actually make an acid. They don't make an ionic compound, but ionic compounds and acids are kind of similar in the way that they behave. And calcium and sulfur do make an ionic compound, even though they have a closer electronegativity difference. Now, we did also discuss, so that is how you determine if it's going to be ionic covalent or somewhere on that spectrum. We also discussed the fact that some elements might be polar and some elements might be nonpolar. So in that case, elements that are polar, that just means that they're going to have a heavy electron side. And that's going to be kind of like oxygen and sodium. Sodium has a 0.9 electronegativity and oxygen has a 3.5. So the electrons are going to want to flow to that side. They're going to want to go toward the oxygen because the oxygen is more attractive. So that means that if you were to look at this and look at its charges, you would have sodium here and oxygen here, and you would end up having, let's say we call this our electron cloud more, and so you would end up having a really thick electron cloud here by oxygen because sodium is not attractive to the electrons. It has a very low negativity. If we were to look at, let's say, hydrogen and carbon and hydrogen's electronegativities are so close that when you watch the electrons distribute themselves, they are going to distribute themselves more evenly around both elements because of the fact that neither one of them has a significantly different electronegativity than the other one. So that is your difference between polar and nonpolar. Same thing if you were to look at hydrogen and fluorine. Fluorine is, again, super highly electronegative. So the electrons are going to want to hang out by fluorine significantly more than they're going to want to hang out by hydrogen. So there's going to be a big electron cloud all around fluorine versus very little around hydrogen. So this would be considered polar, this would be considered polar, and this would be considered non-polar.